Welcome to this explainer. If you're designing, building, or scaling modern distributed systems, you've inevitably crashed into a massive architectural crossroads. How do we actually handle all this data? Today, we're settling the debate on two absolute giants in the industry, Kafka and RabbitMQ. I'm going to walk you through the architecture of these real-world systems, compare their raw benchmarking performance, and give you the exact blueprint for which one actually belongs in your stack.
But first, just picture this. Imagine your application suddenly receives 1 million requests per minute. It's an absolute back-end nightmare, right? Orders are flooding in, payments are processing, email notifications are firing off, and analytics events are just streaming continuously. If your architecture tries to process every single one of those tasks immediately, synchronously, well, your servers are going to melt down and crash. So how do massive companies like Netflix, Amazon, and Uber survive this? It's simple. They don't process everything right away. Instead, they decouple their systems.
Okay, let's dive into this. Here's the game plan for our explainer today. First, we'll establish our baseline by looking at the message broker solution. Then we'll unpack the architecture of RabbitMQ, our smart router, followed by Kafka, the massive log. After that, we'll look at some hard data in a performance head-to-head. And finally, we'll break down real-world architecture choices so you know exactly which tool to use. All right, kicking things off with Section 1, the message broker solution. Before we actually compare these two technologies, we have to understand the foundational problem they're solving. Think of a super busy restaurant. Customers are placing orders left and right. Now, if every single customer walked directly into the kitchen and shouted their order at the chef, chaos would ensue, and absolutely no food would get cooked. Instead, orders are written down and placed on a ticket rail, a queue. The kitchen then pulls and processes those orders safely, one by one. Well, a message broker does exactly this for our software applications. It acts as that crucial middleman, taking the heavy load off your processing services.
The data flow here is incredibly elegant. In Step 1, the producer, say your web application, sends the messages. In Step 2, the broker receives and safely stores them. And finally, in Step 3, the consumer, which is your backend microservice, processes them at its own pace. This decoupling directly improves scalability, provides fault tolerance, and completely prevents those dreaded system crashes during huge traffic spikes.
Moving right along to Section 2, RabbitMQ, the smart router.
So RabbitMQ is one of the oldest, most battle-tested traditional message brokers out there. And honestly, the best way to think about it is like a highly intelligent post office. Its absolute primary goal is guaranteed, precise message delivery. It receives a package, looks at the label, and uses a really complex set of rules to push that package exactly where it needs to go.
Under the hood, RabbitMQ relies heavily on the AMQP protocol, and its absolute secret weapon is something called an exchange. When a producer sends a message, it doesn't just go straight to a queue. No, it goes to an exchange first. You can kind of think of the exchange as a set of routing rules. You've got a direct exchange for exact routing keys, a topic exchange for wildcard matching, a fan-out exchange if you just want to broadcast to every connected queue, and a headers exchange for routing based on specific message attributes. It is incredibly flexible. Because of all this routing intelligence, RabbitMQ is your absolute go-to when every single message matters. Imagine an e-commerce order. One single checkout event needs to trigger a payment service, update the inventory service, and fire off an email confirmation. RabbitMQ routes these messages precisely, and here's the kicker. It requires an acknowledgement from the consumer before it actually deletes the message. If the consumer crashes, no problem. RabbitMQ safely requeues the message. It is literally designed for maximum reliability.
All right, let's switch gears. Section 3, Kafka, the massive log.
Now, Kafka was originally developed over at LinkedIn to handle a completely different scale of data. If RabbitMQ is our smart post office, you should really think of Kafka as a giant, immutable library logbook. It's not just a queue, it's a full-blown distributed event streaming platform. Instead of routing and then deleting messages once they're read, Kafka just appends events to the end of a massive log file. It offers infinite retention, which means your consumers can literally go back in time and replay historical events whenever they want to.
So the crucial point here is understanding this high-contrast architectural binary. RabbitMQ uses a push model. It actively pushes data to its consumers. It acts as a smart broker managing dumb consumers, and its messages are transient. Once they're processed, they are gone forever. Kafka, on the other hand, is the exact opposite. It uses a pull model. Consumers fetch the data only when they are ready. Kafka acts as a dumb broker with smart consumers that track their own read positions or offsets. And its messages? They're persistent event logs that stay right there on the disk.
Now you might be wondering, how does Kafka handle millions of messages a second without breaking a single sweat? Well, it all comes down to its scalability secrets. Messages are stored in categories we call topics, and these topics are broken down into partitions. This is huge because it allows Kafka to scale horizontally across tons of servers. On top of that, Kafka writes data sequentially to disk. Sequential disk I/O is blazing fast, which basically allows Kafka to bypass standard memory limitations entirely. And since consumers track their own offsets, the broker itself does almost zero computational work during a read.
Let's look at the numbers. Section 4, Performance Head-to-Head.
Now, what's really interesting about these exact benchmarking figures from Confluent, who tested these systems on cloud hardware, is the staggering difference in peak throughput. When pushing these systems to their absolute limits, Kafka hit an incredible 605 megabytes per second. Meanwhile, RabbitMQ capped out around 38 megabytes per second. Why such a massive gap? Well, because RabbitMQ relies heavily on CPU-intensive routing and single-threaded queues, which really limits its vertical scalability. Kafka's partitions, sequential disk log design, it simply dominates at massive volumes.
But hey, throughput isn't everything, right? Latency absolutely matters, especially if you're dealing in real-time AI systems or fintech. And here is the real nuance. RabbitMQ is the absolute king of speed, achieving sub-millisecond latency, but, and this is a big but, only when the system is lightly loaded, say around 30 megabytes per second. If you overload it, that latency spikes. Kafka, because of its poll model and batching, has a slightly higher baseline latency of around 5 milliseconds. However, it sustains that low latency even when it's being completely bombarded with a massive 200 megabytes per second load.
Bringing it all together in Section 5, Real-World Architecture Choices. So how do we actually use all this information to make a final decision for our own stacks? Looking at the bigger picture, if your architecture demands complex routing, immediate push-based delivery, and guaranteed execution for critical things like e-commerce payments, banking, or real-time user notifications, RabbitMQ is your best friend. But if you are building massive AI training pipelines, ingesting telemetry data from millions of IoT devices, or you need the ability to replay historical event streams, Kafka is the undisputed champion.
The truly beautiful thing here is that you don't necessarily have to choose just one. Lots of massive enterprises use both, putting each exactly where they shine. But it all comes down to really knowing your data flow. So I'll leave you with this. If your next project suddenly scales to 1 million users tomorrow, do you know exactly how your architecture will handle the load? Take these concepts, apply them to your own backend, and build systems that never crash. Thanks for hanging out with me on this explainer, and keep building brilliant architectures.